So it is my pleasure today to introduce our speaker, Jan Hankendi, who is a postdoctoral researcher working with Aisha across the street. But as Ija was just telling me, his office is a little bit farther away in San Diego, because you're in San Diego visiting company or
No, I was based in San Diego, so I stay there.
stay there. All right. So please welcome Jan, who has traveled all the way from San Diego to give this talk today. And yeah, let's get right into it. So please take it away.
All right. Thanks for the introduction. It's so good to be back in Boston. So I got my PhD in 2015. So yeah, I'm back after 10 years as a postdoc. So today I'm going to be talking about the challenges in the growing data center electricity consumption. And also this electricity consumption brings some sustainability challenges. And I'm going to be basically talking about how we can tackle these issues through building tools and investigating the life cycle of data centers. So data center electricity consumption has already been a big problem over the last couple of decades. But now we are entering a new era, which is the exploding demand on data center resources because of the AI applications. So the question is, how do we meet these growing demands on data center resources without really impacting the environment, also without pushing the grid, impacting the grid stability? So these are two important questions. One is the sustainability, the other is the problems that come with the grid stability. So in this plot, this is a plot from Everett from 2024, and it's showing the US data center electricity consumption, and it's basically showing how this demand is expected to grow by 2030. So Everett is doing four different scenarios, evaluating four different scenarios from low growth to higher growth. So low growth is basically before ChatGPT or these popular AI tools were introduced. So the expectation was the data center electricity consumption is going to be growing around like 4%. But after this introduction of the LLM tools and the explosion of AI, they revisited these scenarios and the growth rates, and now they are expecting to see high growth around 10% and higher growth with 15%. So the difference between high and the higher growth is that in the higher growth case, they are basically doing some pessimistic assumptions about how AI is going to impact the electricity consumption. And in the high growth case, they are also including how AI can help improving efficiency. So the electricity consumption is not as bad as the higher growth case. But either case, if you look at this plot, we are seeing this exponential growth expected in the next 5 to 10 years. And the other problem is in the US case, if you look at the plot, the map on the right, it's showing the percent of data center electricity consumption in each state. And if you look at Virginia, which is a data center hotspot, it's expected to consume, data centers are expected to consume more than 20% of the overall electricity consumption. So this basically affects the grid stability and pushes it to higher stress. And we need to solve these challenges by understanding the data center operations and understanding the life cycle of data centers.
In those other states, it's just because they are sparsely populated and therefore.
Yeah, this is kind of an interesting case. This is North Dakota, and it's basically there are really high tax incentives. That's why the expectation is higher on this region, similar in other regions.
Let's say because cows don't consume electricity.
Yeah.
Forgive the slightly cynical question, but isn't your time more effectively used trying to improve AI energy use rather than data center energy use?
That's part of it actually. I'm gonna talk about that issues as well. Okay. Actually, we did some projections on that, looking at further like 2050, and we are seeing if we include all the AI improvements and efficient AI use, we kind of expect to see around 30 to 40% reduction in the overall growth by 2050. But yeah, that's a good point.
Well, there could be one revolutionary new idea out of kind of thing.
True, exactly, true. So as I said, this adoption of AI tools are exponential, and everybody is using these tools. And even for non-technical people, use of these AI tools are pretty straightforward, and it really feels so natural to interact with these really advanced tools through language and language models. So this basically derives the exponential increase in the data center demand. And the real problem is, if you look at this plot, it's showing the energy consumption of the traditional Google search versus AI-powered Google search. So Google now is including in their search, they also provide you some AI driven answers. So if you look at the energy consumption, it's more than 10x compared to the traditional Google search that we used to do by just typing some queries on the browser.
To do so many times less search.
Yeah. So there's also this projection about if all the Google searches are turned into an AI query, we expect to see, and there are like 9 billion of Google queries every day. The yearly extra energy consumption is expected to be around 10 terawatt hour, between 10 and 30 terawatt hour. So this is a huge burden on the grid, as well as the portion of data center electricity consumption compared to the pre-AI era. So this plot is basically actually on the right is showing how the AI is going to push the boundaries of data center power demand in US, also in the world. So if you look at here, we are I mean, without excluding the AI, which is this blue line, we are around 300 terawatt hour. But with the inclusion of AI by 2030, we expect to see this number to reach to 400 terawatt hour. So these are huge jumps in the electricity demand, and there should be some solutions and really investigation into how data centers operate and how can we understand better their sustainability impact. So understanding the overall environmental impact of a data center requires investigating all the life cycle stages of a data center. So this is basically illustrating all 4 main stages of a data center. I divided into divided into embodied and operational footprint. When we talk about embodied footprint, it's basically the material extraction, the mining and processing of the materials, plus the manufacturing of the IT devices, equipment, power infrastructure, cooling infrastructure, as well as the building the data center itself. So embodied footprint is pre-use of, it's basically derives the environmental footprint before data center starts to operate. And after we build this data center, put all those IT equipment, then we're going to look at the use phase, which is basically users are running their workloads, and which is basically called the operational footprint. Most of the research goes into the operational footprint and how to optimize data center operations. But as I'm going to show in the next slides, embodied footprint is also a growing concern when building and operating data centers. And at the end of life stage is the phase where we reuse the hardware, repurpose them, recycle them, and then we are trying to reduce the overall environmental impact in this stage. So one of the issues is that understanding or analyzing the life cycle of a data center requires lots of different data. It ranges from hardware vendors, how the infrastructure is built, how the data center is operated, and also how big tech is utilizing their hyperscale data centers and how they are optimizing their operations. But this data is usually not available to researchers. So there's a huge problem with data transparency when we are trying to optimize the data center carbon emissions. So how can we tackle this problem? So in the face of these data gaps, we need some tools that will require minimal data and that will provide you some first order estimates and approximations about what the carbon footprint of a data set is. So we built this carbon meter tool, which is a carbon footprint calculator for data centers. And this is an open source tool, which can be expanded by researchers or integrated with other tools, which is the end goal and the big vision is basically integrating this tool with other tools as well. But this is our first attempt to create a carbon footprint analyzer for data centers. So this is a screenshot from that tool. On the left, this is how we calculate the embodied footprint. This tool basically provides all these adjustable knobs to the user. And the only thing you need to get an overall estimate of the data center carbon emission is that the power capacity, and the second is the data center area. Yeah.
So did you build the models that back this tool off of the data centers you talked about in the previous slide?
Yeah.
So you collected data centers from a very, I guess, climate homogeneous area and places that have different, a very different energy policy in this country for the model. So
yeah.
Does this model relevant to U.S. data centers?
Yeah.
I think I got to believe there's very little in common from something that sits in Norway and something that sits in Arizona.
That's a really good point because I'm going to show some results from Norway and the US also. So this tool allows you to do analysis on different locations. So it's not specific to one location.
So are you interested in energy use or carbon footprint?
So carbon footprint, it's doing both. The energy is coming from the operational footprint, but in addition to the operational footprint, this tool also does the embodied footprint estimations. So when we say the embodied footprint estimation, it's like how much you are emitting through manufacturing these devices, servers, network equipment, even the building the data center itself. Concrete has a good big carbon footprint. So it kind of all includes all those factors.
It's true, but it's a one-time carbon footprint.
True. That's why it's actually a smaller percent, but it's still part of it. So we wanted to provide, I talked about the life cycle, all those 4 stages. We wanted to include all those stages to get a good estimate of what's the overall carbon footprint. So in the embodied footprint, after you enter the power capacity and the data center area, we can make some estimations about how many servers can you deploy in this data center. And based on how many servers you deployed, how many network equipment you're gonna need to connect all those servers and make it operational data center. So by just inputting these two, power capacity and data center area, this will allows you to estimate how many servers you can deploy based on your network topology, how many switches are going to be required. And in the end, it gives you the embodied footprint of a data center. And in here, it's showing also based on the data center area, what's gonna be the building construction footprint of this construction. So for the operational footprint, you basically need to provide, or this is an adjustable knob, so it's not really hard-coded or anything. But based on your location, the energy source, carbon intensity of the energy source is going to be different. As you said, in Norway, this number is going to be low, but if you go to Germany or even go to Virginia, these numbers, the carbon intensity is going to be way higher. So this tool basically allows you to change the energy source carbon intensity, so you can evaluate different locations and then get an overall idea about your operational footprint. And this is an example breakdown of operational footprint versus construction versus the embodied footprint. This is an example with showing 92% operational footprint versus 7.8 embodied footprint. So so we put this tool into work by looking at 36 data centers, first in Europe. We started with choosing 15 real data centers from Norway, 15 from Germany, and 6 from Denmark. And this plot is showing the power capacity in a data center area of these data centers we chose. We tried to choose high power capacity, low power capacity, large data center area, smaller data center area to be able to provide a full picture of depending on what size of data center or what power capacity you're using, how the carbon emissions are going to be changing.
So with respect to the power capacity, do you have a capacity factor as well that you have to take into consideration, or are they always running at 100?
No, yeah, that's also an adjustable knob in the tool. So this is the maximum power capacity, but obviously it's not running at the maximum power capacity. So there are some adjustments that are made within the tool that tells you how much power you can allocate to servers, how much power you can allocate to network devices, how much power you need to allocate for cooling, for instance. So this is just the maximum power capacity, but there are adjustments within the tool that kind of reduces this number and distributes it across different hardware and cooling and the power infrastructure. The reason why we chose these 3 different countries, Norway, Denmark, and Germany, is that the energy sources are different. For instance, Norway is running almost 100% hydro, so it's known to be the greenest country in terms of the carbon intensity of their energy sources. And then Denmark is more like a mixed country, a little bit higher carbon intensity. And Germany is one of the highest in Europe. So we wanted to look at how these energy sources are also affecting the overall carbon emissions. That's why we chose these 3 countries. So in addition to the location, there's also another factor that hugely impacts the overall carbon footprint of the data center. Yeah, go ahead.
I actually have a question from like 2 slides ago. When you say operational footprints, like I'm seeing a large green chunk. Do we know the maybe smaller labels of what causing that much footprints?
So it's actually not always this large. I'm going to show in the next, actually in that couple of slides later. This number depends on where you're running the data center. Because if you're running a greener country, your operational footprint is going to be lower. And then embodied footprint is going to be a larger percentage of the overall carbon footprint. So this number is basically driven what location you're running, what kind of servers you're deploying, and what size of data center you're operating. So this is just a sample. But if I go to this slide, this is actually showing it's not always it's always dominated by operational footprint, but it's not always that extreme. So one of the features of carbon meter is that it allows you to choose different types of servers. So in this study, we are looking at 3 different servers. One is a little bit older, like almost 10-year-old server, which is commonly deployed in data centers, which is Dell R710. And then we're looking at a more recent and higher end Dell model R740. And then in the middle, we have an HP server. So all these server decisions also affect how your footprint is going to be changing. Because when you have a higher storage, for instance, your embodied footprint is going to be much higher than running at a smaller storage. Storage is the main driver of the operational of the carbon footprint of server manufacturing. So this plot is basically showing that this is the total footprint breakdown of Norwegian data centers based on 3 different servers. So if you look at the small storage Dell server, operational footprint is almost accounted for 95% of the overall footprint. But if you go to a higher end server with a large storage, 24 terabytes, then you're going to see embodied footprint becomes 35%. And this number is actually expected to grow because storage needs are also expected to grow. And the reason why we are looking at the Norwegian data center is that in the future, renewables are going to be taking a much larger percentage of the overall energy generation. So we are trying to see in the future how these numbers are going to be changing. So probably on the right-hand side, this large storage Dell server is a more representative of how it's going to look like in the future. So these are all the results that are the output of the carbon meter tool. Yeah.
Good question. So you said that more storage means more impact, and yet your graph shows exactly the opposite. The server with the smallest storage has the largest impact.
When you say what is the large, when I say the embodied footprint is going to be larger, because storage is,
Sure, but that's not
the
like,
embodied.
but the operational is not.
because the embodied is the larger becomes a larger percentage if you use larger storage.
Necessarily, if you're using it, then your embodied will be larger, but the daily use would be higher.
Yeah. This is not showing the comparison between the overall footprint. This is showing how the breakdown is going to change when you're deploying different types of servers. So if you deploy larger storage servers, your embodied footprint is going to be a higher percentage of the overall footprint. I don't know if that answers.
100% for one.
Yeah, it's not.
100% for the other.
Yeah,
It's just whatever the.
that's a good point, actually. Maybe we should also provide a plot that shows how they are relatively changing.
And the absolutes.
Yeah.
What's important, right?
True,
I use
yeah.
1 milliwatt of power, I don't care.
True.
if it's
Yeah,
all embodied.
exactly. Yeah, that's a good point. That's a good point.
Operational here consider also cooling, right?
Yeah.
But you're doing over 4 years.
Mhm.
So shouldn't you also start to account for climate change effect on that?
If you can predict it, yes.
I mean, 4 years, maybe it's not a long time, but yeah. Yeah, maybe, but yeah, 4 year, maybe we are not gonna see that much fast change in terms of the overall
The
climate.
society breaks down.
Question, if you're dominated by the operational footprint, then that means that economically speaking, you have a lot of freedom to throttle down when you don't like the cost or source of the energy.
True.
An AI workload for inference is especially conducive to throttling down because it doesn't keep much state.
Right.
So if you're dealing with a power source which is poorly correlated with the rest of the demand, then can you just shut it off when people run their ACs or when it's night and your hydropower is not utilized?
True. Actually, towards the end, I'm going to show you some results how we can actually adjust these power usage, and then that way you can also reduce the grid impact on the grid stability, and reduce your energy costs. So there are ways to do it, which I'm gonna talk towards the end of this slide of this talk. But yeah, that is.
Does the tool account for these?
No, this is not integrated. This is a separate tool, I would say. So in this current version, we are not really looking at those both impacts. But I'm going to show you also there are some opportunities by using this tool to reduce the overall emissions. So it's not just analysis. I'm going to show you the version 2 of the tool in a couple of slides later, which also shows you how you can reduce the overall carbon emissions by doing some intelligent workload migration across different regions, so that you can balance or reduce the overall impact. So, and in the tool, we are also looking at these two different parameters. One is the lifetime of your hardware, and the other is the utilization level you're running your servers. So these plots are showing how the overall carbon footprint is going to be impacted if you are able to run your hardware for a longer time, let's say from 4 years to 8 years. And if you are utilizing resources, utilizing your servers at a higher level, from 50 to 80%, you are going to be able to reduce your overall carbon footprint close to 30%. So these are really important parameters to consider when you're trying to optimize your data center operations in terms of the carbon footprint. But if you look at these, one of the other takeaways from this slide is we are looking at Norway, Denmark, and Germany. So Germany has the highest carbon intensity. So for locations that have higher carbon intensity, even if you optimize for lifetime, even if you optimize for utilization levels, the impact, the reduction in carbon emissions is going to be limited. But if you look at Norway, you're going to see that it makes a huge difference when you are running it on a greener energy flow.
A quick question, particularly on the utilization aspect here. Like, people who run data centers do this to make money. Why would they design a data center with a utilization rate of 50%, essentially giving up 50% of the work that they could be doing?
So they are not really designing, but there's also the usage patterns. So that it's not always up to the data centers. It's also how many people are, there's also the time of use impact, how this utilization level changes. When people are sleeping, for instance, you're going to see that utilization level is going to be low. So they design these data centers to be able to respond to high demand phases as well. So during the day, there's going to be low demand phases and there's going to be high demand phases. So in those low demand phases, you might see actually like as low as 40-50% utilization levels. But it's designed to respond to high demand usage. So that's kind of like 80 to 90%. So it's designed for that, but it's not always running at those levels time of the day. So this the results I showed you was the carbon meter version 1, which kind of allowed you to do these like quick analysis on operational footprint and carbon footprint, the embodied footprint. And then we start working on the version 2. And the version 2 is trying to minimize the carbon footprint as well as the electricity costs through workload migrations across different locations. So we integrated two real-time data. One is the carbon intensity data provided by electricity maps. So this is fed into an optimizer within the carbon meter version 2. And then the electricity prices from Statnett, which is the Norway's ISO. But I'm going to show you also the US case studies and how workload migrations and the electricity cost can be optimized or reduced by using this new features of the carbon meter. So the problem formulation is we have some constraint, workload conservation constraint, which is the total power required for workload never changes. And then user can adjust these utilization bounds between 30% to 90%. This can be any number. User can do 60 to 70, 80 to 90, but these are the initial assumptions for the utilization bounds. And what we are trying to minimize is this weighted sum of cost and carbon emissions. When I say cost, it's the electricity cost. So we have two weights here, W cost and W carbon. So for instance, if the sum of the W cost and W carbon is 1. So let's say user can adjust these rates depending on their priorities. For instance, if they want to purely optimize for carbon emissions, they're going to set W carbon to 1 and then W cost to 0. So your objective becomes just minimizing the carbon emissions. But if you want to do some more balanced optimization, you want to optimize for or minimize both carbon emissions and the electricity cost, then user is able to put 0.5, 0.5 to each of these weights, and then you're going to be doing some more balanced optimization. So this is the case studies that we did for European data centers, again, Norway, Denmark, and Germany. And this plot is showing you how the carbon intensities are changing daily during a year. So this is data from 2023, and it's showing Germany is always the highest and Norway is always the lowest. So this might not look that interesting, but the electricity prices are not always one-to-one correlated with the carbon intensity. So there are some opportunities when you consider the electricity cost minimization. There are some opportunities that arise when you're optimizing for both carbon emissions and the electricity costs. So for the case study, we chose 3 different data centers from each of these regions with different power capacity and different carbon intensities. And we tried to choose like 1 small, 1 medium, 1 large from each of the countries. And we wanted to see how the maximum reductions in electricity costs and the carbon intensities are going to look like when we enable workload migrations between 2 data centers. So this plot is showing the electricity cost and carbon emission reductions. So if you look at on the left side, these are 2 data centers in Norway, Oslo 1A and Oslo 4C. These are the actual data centers. And if you enable workload migrations across these 2 data centers, you're not going to be seeing much of a reduction because these are very similar in terms of the carbon emission, carbon intensities, and also the electricity prices. So you're not going to be seeing much reduction. But if you look at on the right-hand side, these are also 4C, Norwegian data center, and Düsseldorf, German data center. And then you're gonna start seeing close to 60% carbon emission reductions due to the lower carbon intensity in Norway versus the higher carbon intensity in Germany. So the assumption also under this migration cost is that you can only migrate certain types of workloads. So if you have a batch versus latency sensitive workloads, you are going to only be able to migrate batch workloads because the performance requirements of latency sensitive workloads are much higher. So we just named or categorized those benchmark or workloads as not migratable because they have strict QoS requirements. So if you have batch workloads, which are long running workloads that are not really sensitive to QoS, then we consider those workloads as migratable across 2 different data centers. And the another factor is the impact of seasons. So depending on the season, your carbon intensity is going to be changing. Sometimes you're going to be using more solar, so your carbon intensity is going to be lower. But sometimes in winter, for instance, you're not going to be using solar, so your carbon intensity is going to be higher. So this plot is showing how the seasonal carbon emissions are impacting the overall reductions. So this is considering 2 data centers, 1 in Norway and 1 in Denmark. And if you do these migrations, enable these migrations during spring, you're going to be seeing a maximum of 13% carbon emission reductions. But if you do it during the winter time, you're going to be seeing higher reductions because in winter time the carbon intensities between Norway and Denmark is higher, so there is more room to optimize or minimize the carbon emissions. So there's a huge impact of the seasons also. So when you're making these decisions, you got to also consider the seasonal impact on carbon emissions. So another factor, as I was already talking about, the type of workload or the workload mix that you're running in your data center. So for instance, if you're running 100% batch workloads, which are all migratable, then you're going to be seeing obviously higher carbon emission reductions and also higher electricity cost reductions. So this plot is showing the percent of batch workloads in your workload mix. So if you're at the high 100%, you're going to be seeing the highest reduction. So the goal of this plot is to show how your workload composition or the workload mix can also affect your reductions in electricity cost and carbon emissions. So for instance, if you look at the 100% case, you're going to see around 70% reductions, but you are mostly running latency sensitive workloads, your reductions are going to be limited to around 5 to 6%. So there's a huge impact on how you decide to distribute your workload in your data centers. And then if you enable workload migrations in heavy batch workload data centers, you're going to be seeing higher reductions. This plot shows that high dependency on how your workload mix is affecting your carbon emission electricity cost reductions. So another feature that we added to this workload migration optimization is the latency. So we consider 4 main components in that affects the migration cost. One is the data transfer time. The other one is network latency. And then sometimes you need to restart the compute nodes. And then there's also when you start running a workload on a new data center, there's going to be some scheduling overhead. So we added these migration latency impact, and then we are start looking at US data centers and see if there are opportunities in US when we consider this workload migration latency in our optimization problem. So this is a plot showing 7 different ISOs in the US, and we assume just a single workload assumption, which is a small size LLM. It's running around 100 hours, and with a data set size of 2 terabytes. These are all adjustable knobs, but this is just to show you an example how this looks like. And just to give you an idea how to read this plot, if you look at California ISO, the y-axis is showing the overall workload migration cost, and the x-axis is showing how you're defining your weights for electricity versus carbon optimization. So 0 means you are purely optimizing for carbon, and 1 means you are purely optimizing for electricity costs. So if you look at the California ISO, this yellow line here, if you're trying to optimize for electricity, you're always better to migrate your workload from California ISO to other regions. But in this cutoff point, below these points, you're going to see that you're basically optimizing more for the carbon, and then sometimes you are better off when you decide to migrate from, for instance, from MISO to California due to their carbon intensity sources, carbon intensities. So this is showing the overall big picture from 6 different ISOs. So it's basically, let's look at this one from CAISO. What is the best region depending on the season? So each of these rows are winter seasons: winter, spring, summer, and fall. And then on the x-axis, we are looking at different migration penalties from 0% to 10%. So 0% is not realistic, but we wanted to show how it affects. So and it's also showing what's the best region to migrate from CAISO under these conditions. So if you have a high penalty and you're trying to optimize for electricity in winter, you're better off when you are migrating from CAISO to MISO. But if you start to optimize more for the carbon, then you're going to see you're better off without really migrating. So this plot is showing how these patterns are changing depending on the season, depending on your optimization goals and depending on your location. So I have not, yeah, okay, I almost like getting to the end of slides. So one of the other things that we've been looking at is utilizing demand response programs to basically help stabilize the grid, and also while reducing the energy cost of data center operations. So we are specifically looking at AI workloads and how data centers participation in demand response programs can impact their electricity costs. And we are looking at two main demand response programs. One is the regulation service reserves, and the other is the emergency demand response. So to do that, we first profile real workloads on real hardware. These are four AI workloads. Three of them are LLMs. One is the vision model, and these plots are showing the power versus performance on 4 GPUs and 8 GPUs. These are all profiled on real hardware and using NVIDIA P100 GPUs. And we plug these profile numbers and then evaluate how we can participate in demand response programs to reduce our energy costs. So this is showing when you're participating in demand response program, you are expected to track a certain power target. So this plot is showing that power target coming from the ISO, these dashed lines with the red, and then the actual power consumption is shown with the blue line. So the closer you are to the power target, the more you're gonna reduce your electricity cost. So this is basically shows that we are able to track pretty well the power target so that we can maximize our electricity cost by participating in demand response programs. So I'm gonna skip to this one. So this is showing overall cost savings when we are participating in different types of demand response with different types of workloads. So these are all different workload compositions. WTrain is you're just running training workloads, and this inf is saying that you're running only the inference workloads. And energy cost savings basically varies hugely depending on what kind of workload composition you are running, workload mix you are running, which was also the takeaway from the workload migration case. But the maximum number is above 60%. So you're able to, if you participate in these programs, you're able to reduce your energy cost by up to 63% for training workloads.
What's the difference between the programs?
So programs provide different incentives. So emergency is they provide different cost models. So if you are participating in an emergency program, you are expected to respond to these emergency, and you need to reduce your power consumption below a certain threshold. But if you're participating in an RSR program, you're expected to track a certain power signal. So it's not a constant signal like the emergency, but it's more adjustable ISO signal that comes to your data center. So and they have different cost reduction models that comes with the depending on the program. For emergency, you are getting higher incentives because it's a more emergent case. But for the RSR, you're expected to track this signal so that the grid can stabilize its operations. And then it gives you some financial incentives to do that. We did some proof of concept implementation on real hardware of this of the demand response participation. I'm not going to go into details much here, but I'm just going to show this plot is showing within 1 hour we are receiving some power target from the ISO on a real hardware, and then we are able to track pretty accurately even on a real hardware, which kind of shows promising results. But the future goal would be running at a higher number of GPUs, so the realistic impact will be more obvious when we have those larger number of GPU experiments. But this is just the proof of concept that it can be done on real hardware as well.
So how do you track this thing? Like just do you adapt the frequency or
Yeah, for
you
the
don't care about any SLA or?
no, there,
could be
no, there are some QoS requirements defined for each of the workloads. So when you're running multiple workloads in your data center in different GPU nodes, depending on the QoS requirements of the application, you're going to allocate more resources to one that have more strict QoS requirements. So I didn't go into those details, but the overall framework handles that, and it tells you how much resource or how much weight you need to allocate for a certain type of workload to satisfy the QoS requirements. So it's in the tool, but yeah, I didn't get into that details for the time concerns. Okay, so finally, where do we go from here? So this is our roadmap for from 2025 to 2035. So what should we do in the next 10 years to achieve net zero in the era of AI? So some companies like Google were claiming that they were going to be net zero by 2030, but during last year, they publicly announced that they are not claiming to be net zero because now they are dealing with the challenges due to exploding AI demand. So,
Sorry, I never understood this. How can you be net zero if you produce anything? Does that mean you just offset the carbon with like credits or something?
yes, that is.
So it's not really net zero.
Yes, that is one way.
Paying for the right to pollute.
True. That's actually why Google stopped claiming they are going to be net zero, because they used to include those carbon offsetting and carbon accounting strategies into their reporting, which is kind of the trick. But now they are taking a step back, and then this doesn't really make sense. It's not really net zero, so we're not. They are saying they are not going to be net zero by 2030. So these are three phases that we put together. So the first phase basically highlights this improved transparency, real-time carbon tracking of data centers, and then using more efficient models and more efficient computational models. So this is a short-term transparency and accountability phase. In the second phase, after like 2-3 years, the system-wide integration is essential, and then we need to start looking at how we can improve the circular hardware usage, and also how we can integrate more extensive carbon footprint databases so that the researchers and companies can start optimizing in a realistic scenarios. And finally, we expect some AI impact start to impact the overall carbon footprints. The improvements in hardware design, software design by employing AI techniques, and also there should be some policy implementations like verified removal credits, maybe some emission caps for AI development. But this whole requires a collaborative process between researchers, corporations, and also the policymakers. So this is a 10-year plan that we kind of envision to happen in the next 10 years, but things are changing so fast. So maybe next year this is going to look different, but this is how we envision right now. So to wrap up, what I did in this talk is to talk about growing sustainability concern in data center industry, and the exploding AI demand is driving this unexpected increase in electricity consumption. And I talked about the data gaps and data needs that need to be transparent to researchers so that we can build tools and techniques that are realistic and that are applicable to real life cases. We introduced this carbon meter tool that allows you to do LCA analysis, as well as quick analysis on how workload migrations can help you to reduce electricity costs and carbon emissions. And finally, I shared our results on how data centers can participate in demand response programs so that they can help grid stability, as well as reduce their costs, as well as the carbon emissions by participating in these programs. Yeah, I think that wraps it up. If you have any questions, I'll be happy to.
I got a quick question with the sustainability angle of this whole thing. To me, sustainability means that you kind of can keep doing what you're doing. I mean, making it better and yada, 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 but you can keep the trajectory that you're on. If you're looking at your power growth forecast, they grow exponential. And for the first part of your talk, you show like power savings capacities of 30 or 60%. If your power demand grows exponentially, it doesn't matter how many percent you save, you're not going to be sustainable. You will crash a little later, but that's not sustainable, that's efficiency.
True. I think maybe I didn't mention in this talk, but there are also other factors like more integration of renewables. Some countries are really pushing for nuclear, for instance. So the energy generation, electricity generation techniques are going to be also changing in the future. So that is kind of expected to offset that exponential growth. And then there is also the AI-driven improvements in efficiency. So when you include all those improvements, the expectation is that it's going to offset that exponential growth. And this exponential growth is not expected to continue forever. There's always this initial ramp-up period, and then certain things are going to saturate, like we saw when first like Google and Google search and also the social media became popular. There was a huge ramp, and then it didn't really jump after a certain period of time. I think in the first slide, it kind of shows here, if you look at here, from 2000s to 2020, the overall electricity consumption is kind of jumping in this case, and something ramping up from 2000 to 2005, but then it kind of plateaus after 2010. So similar behavior is expected for the AI adoption, I guess, and also the integration of different electricity generation mechanisms are going to offset this exponential growth. So
fusion is going to save us.
Who knows? Hopefully, I don't know. But yeah, there should be improvements in all aspects. It's not just data center operation or these migration techniques. It should be all like hardware, electricity generation, and the policies. They all need to work together to offset all these exponential growth.
Kind of piggybacking off of that, how much of the study looks at the energy recapturing? I know some data centers are trying to incorporate their hot water outflow into like the public municipality.
Right.
And so that would in turn be a more sustainable approach.
Right. So it's basically covered in this end of life cycle stage. And in the tool, actually, I maybe didn't talk about, but we include this water usage effectiveness metric to incorporate how they can reduce the overall energy impact. But if you look at this recycle phase and compare it to the impact of reducing the carbon emissions, it's really not that much. What we are seeing is around less than 2%.
But is that the recycling of the materials that make up the data center, or the actual energy that goes into the data center?
It's mostly the materials. It's
so not when the data center is actively in use.
Right. Yeah.
Oh, okay. So
maybe it's not. Yeah.
Maybe in the future.
True. Yeah.
Yeah, I think you want more questions?
Let's look at the, I know it's not on the slides, but have you looked at data centers that incorporate dedicated racks for some for uses versus these smaller data centers that just put everything together, how that impacts?
Right. So it basically comes into these kind of this parameter for rack power. For instance, if you're looking at a Google data center hyperscalers, this number is around more than 25 kilowatts. But if you're looking at the different data centers, smaller size, medium size data centers, this number is around 15 to 10 kilowatt hours.
But like in terms of like overall usage, I would have to get a data center and then to split it up. If it has specialized rack, I would have to split it up in groups of specialized racks, calculate that power usage.
True,
And then do it for every other subset.
true, yeah. Exactly.
All right, yeah, please, thank you again, John.